thing that we have in English problem and in machine learning as well, right? So if you have the data that you have here, the data that we have is actually a pair, but this doesn't need to be a pair, right? So this is thinking about this is a location, right? When the professor have talked about EIT, right? The one of the last example, so the location that you put the electron, right, in here. So Y is the measurements, right? So we always assume that we have n data points, right? The location and the value of that location. Okay, so this is what we call in machine learning training set. But it's just a terminology. X is in some space, right? Typically, for this talk, we're gonna restrict ourselves in the Rn, right? Finite dimensional Euclidean space. And in Y, we also limited ourselves in R, but it doesn't need. You see that actually many results that I'm going to show you later, it doesn't need to be in R. It can be anything, right? It can be in even function space, right? That doesn't matters here. But just for simplicity, you're going to consider this. So in this notation, I'm calling Z to the outer Cartesian product of X and Y, okay? And Z is just a pair. So Zi may be a pair of Xi and Yi. And the superscript is actually the index of our measurements, okay? Okay, so, and this is the key assumption in statistical learning theory or statistical English problem. That is, you assume that your data as IIDs identically independently distributed from some probability distributions. Okay, so assume that we can get randomly. So the EIT problem is actually not quite random, right? But most of the examples in the world is that you can measure randomly from a different location, but it doesn't need to be that way. Machine learning definitely random, right? But this is the typical assumption that we have, so that we can invoke a large number probability theory. Okay, so this is the pi is one we use for as a probability, the joint distribution of X and Y. Okay, so that's the notation that we're going to use. And we also use D for simplicity or for your shorthand notation. Instead of using pi, I actually use D as well interchangeably, right, with a pi. And then we assume that there's there's noise. Of course, actually this is actually a typo here, right? So the observation typically have noise in there, right? But for simplicity, you can consider that actually there's no noise as well. If you are not familiar with statistical theory, then you can consider there's no noise. But what we actually cover noisily corrupted data. So f star is an underlying function, right? Thinking about English problem, Professor have talked about the A. Remember that A in his example, EIT example. A, you can think about this is like A type, right? Some unknown function that you don't know. And you want to reconstruct the functions based on the observation from X and Y here, right? All right, so underlying thing we never know. So, but we can have measurement. So this is the setting that we have in this lectures. And then our wishes. What are our wishes? So we want to find functions, which we call learner here, right? We call a learner. I'm trying to actually give you some terminology here from statistical learning, machine learning theory. They don't call it a solution, they don't call it a function, they call it a learner because this is a machine learning, right? So actually, in a sense, it's actually correct, right? Thinking about this actually very intuitive because you want to learn f star, from the observation X and Y, right? You want to actually understand that relations, you want to find that relation. So we call it a learner. And of course, that learner could actually, in turn, depends on some parameters. If you parameterize, I'm going to talk about that later. We actually parameterize our learner, right, by some parameters, and therefore we're going to learn the learner indirectly through the parameter theta. Okay, so our goal is to actually try to find a learner that could possibly depends on the parameters that is as close as possible to the underlying function f star. Remember the f star for any x, for any new x, new unseen cases that we haven't seen before. Okay, so the second, this is actually a difficult one, right? The second assumption is difficult, or which is difficult. We want the learner f to be accurate called the unknown distribution as well, right? So this is something that we typically don't see from inverse problem theory, right? We want to have the data. We have our f unknown functions is living in some function space, right? We want it to be accurate, but also we want to know that because of the randomness natures, we also want the learner to be accurate for the unknown underlying distribution as well, right? So this is a much more difficult problem than the typical inverse problem that we see, right? And you see, I'm going to show you, because it's too difficult, we're going to ask much less than typically what we ask for inverse problem, okay? Okay, so the practical way to solve this problem, this is one way, okay? It's not the only way, but ideally, this is what we want. Ideally, we only have the training data S. Remember that we have n pieces of data, right? That's the first thing that we have. And secondly, because remember that we have this is the additional thing that we ask for, right? We cannot expect that our learner, so H is our learner, right? Or our approximate solution. We cannot wish that our approximate solution to be close to the unknown function in some norm, right? You see that question mark here, just some norm here, right? In some norm here, in some field. But we cannot ensure that this is actually less than some epsilon, right? The only way that we can actually, a reasonable way to actually ensure is that we want our learner to be as close as possible to the unknown function with high probability. So this is the standard setting of the statistical learning. So we no longer, right? So if you forget about this, this is what we typically have, we want to wish in the inverse problem, deterministic inverse problem. We want the reconstruction to be as close as possible to the unknown, right? Given any tolerance, any error that we want this to be as close. And we want this inequality to be deterministic, right? But within this context, this is not possible, right? The more reasonable way is to have this inequality to holds with high probability, right? That means delta, when delta is smaller, right? We want this to still hold under some condition, okay? And you see that this is the last sentence is also very important. We want this concentration. So by the way, this is called concentration inequality. Okay, so it's not the usual inequality that we see. This is concentration inequality. We want this concentration inequality to hold true, independent of our distribution there. So this is actually very tough, right? It doesn't matter what the distribution, underlying distribution is. We want this to hold, and we want it to be valid for any reasonable F star that we don't know, right? And of course, for some number of training samples. So this is a number of data, right? So for some number of observations, that depends on our epsilon here, of course, right? If we want some certain accuracy, you want some certain probability, right? And you want it to be good for some unknown functions. This number of samples need to be changed, right? It will be a function of these three parameters. Okay, so this is our practical setting in the statistical learning theory. Okay, so this is what we want to heading for. Okay, so that's the setting so far. Any questions so far? Sorry. Any questions so far? Clarifications? Okay, no. Okay, let me continue then. Okay, so definition. So the first definition. By the way, okay. So in my talk, we're gonna avoid all the proof. There's only one theorem that's actually interesting and easy enough that I'm gonna spend out talking about the proof. But the rest, I'm not gonna talk about the proof. And of course, I can happily provide the proof to you later if you are interested, right? And by the way, what I actually showed you here is actually a lecture, right? A semester lecture graduate class in that UT Austin that I teach many years. And for mathematics, for applied math students and for engineering students as well. Okay, so the first thing that I'm going to talk about is the function space. So this is actually the Q here. We call it a space on learner. So basically, thinking about it is a space on functions, right? Which is very big. And of course, H stars. That we want to learn F star, right? Of course, there's actually two settings that I'm gonna try to avoid here. I'm gonna look at a simplest setting. I didn't tell you whether f star is actually inside Q or not. And in our setting, f star could be outside, right? So we just have some space. Well, thinking about a function space that we are looking for our learner or our solutions. Okay, so that's the function space that we're looking for. H star is called the target learner. We're gonna see later. That's our target because this is the biggest possible function space that we care about. That actually change from one problem to another problem, depending on our problem. Okay, so we're gonna talk about it a little bit more. And then what is R here? R is called the risk associated. Let me actually go forward. What is a risk? The typical risk is called L2 risk, right? So if we look at our English problem, I forgot what the English problem, but typically called objective function, right? Or in the machine learning language, it's called the loss functions. This is the loss function here, right? Or the risk, if you wish. So f star is unknown functions. H is our learner, right? And this is the L2, but with respect to the probability. Remember that I assume that Z is R, right? If Z is not R, then you need to have a different norm in here as well, right? But because of R, this is sufficient, and then we take the expectations. This E stands for expectations, right? Over X here. So this is the risk, the L2 risk. Or we can think it's just an L2 norm, right? With respect to the underlying probability. So it's a weighted, right? You can think about this is, let me actually write out a little bit more in a familiar setting for you, right? So the RH, if we have rho, right? If we have rho, that's or the pi. Remember, that's the pi. Actually, so this is nothing more than f star x minus h x square and then pi of xy here, right? And dx dy. Because remember that we're going to do joint distribution, okay? We're going to do a joint distribution, and this is the over omega here. So it's kind of a quick thing about, if you want, you can simplify it, but we typically consider the output as a random variable as well. So if you want to be really simplified and close to what you know, then you can think about this. It's a much easier setting, right? So this is just nothing more than the weighted L2 norm that you typically see, right? If this is 1, then this is a standard L2 norm, right? This is weighted by the probability density. So you can think it that way. All right, so that is our risk. And yes, please.
Squared is outside of the second graph.
Yeah, I'm sorry, that's a typo. Very good. The 2 here must be outside here. Very good. Thank you. Sorry about that. Very good. Actually, you know why? I did it on purpose. Why? Because I want to check to see any of you are awake. And obviously, Professor Tan is awake. Yeah, you must have coffee in the morning. Okay, so we're gonna continue now. Sorry about that. Okay, that's a typo. So unfortunately, Q is typically too big to operate with, right? So we actually typically looking for some function space over which we're looking for our solution, but typically it's very big. Or you can think about our function space is a continuous, right? So we have to discretize. Think about that, right? You have to discretize. Okay, so what we're gonna do? This is the next space is a subset, which they call hypothesis space. Right? So what is a hypothesis space? The hypothesis space in our setting is a subset of the space of all learners that we care about. So let me make an example here. Let's say I make an example here for you as well, right? Let's say Q is C, right? It's a space of continuous functions. So that you will all continuous, right? All continuous functions. Just an example here, over AB, right? For example, right? So typically there are many other settings, but let's say we're going to look at this, right? And H, we can look at the reproducing kernel Hilbert space or H1 here, right? H1, let's say H1 0 between A and B, right? So and this is reproducing kernel Hilbert space. for example, right? So we're going to look at a much smaller space that we're going to operate that actually have properties that we can take advantage of. Okay, so we're going to look for some, they call hypothesis space. So we're going to denote by H, right, is a hypothesis space. So instead of looking for the minimum, right, instead of minimize the risk over Q, which is a larger space, we're going to minimize over a smaller subset of our original function space. And we call it H bar, okay? So remember, H star is our really working point, but we cannot do it. It's typically it's too big to operate, and it's doesn't have a lot of good property for us to operate with, right? So we're looking for something much smaller. And H bar here we call a target learner. This is our target. We want to actually get to H bar. Okay, in general, H bar is not the same H star. Okay, it's not the same. And of course, we're going to see that the risks evaluated H star is less than the risk evaluated H bar, right? Because you minimize this, you minimize over a larger space. You can get lower values, right? This is a minimization over a smaller, so it's actually higher. Okay, so this is important. It's very obvious, but it's important because we're gonna use that later as well. Okay, now the next thing is generalization error. Okay, so this is again just a terminology in machine learning. What is generalization error? What is true risk? They call it true risk as well. Both words used interchangeably. Okay, so we're gonna know F, L, H, Z here is a log function. Okay, for example, our log function is there, right? This is a log functions. And by the way, you see that I'm sorry, I should have clarified with you right here as well. I'm going to use both of these interchangeably while F star, right, is interchangeably. The underlying unknown functions. So this is F star here as well. So the log function depends on, basically it's measure the difference between your learner or your approximate function and your unknown function, like simple. But it's called risk. And the loss functions, right? Of course, it's actually quite intuitive, right? The further you are away from the truth, the further loss that you actually incur, right? So that's the name itself is actually quite intuitive. So the risk, what is the risk? The risk is, so far I show you the risk. Actually, you can see there, right? The risk is the L2 norm. You can think about the L2 norm with this one, or average error. Right? Expectation is an average error. And notice that Z is X1. It's a joint distribution. It's a joint distribution of X and Y. Okay? So the risk is the average error over our joint space, X and Y, okay, of the log functions. Okay, so that's the setting. And they call it generalized loss because you want to evaluate for all. Right? Remember that the training data only N, but we take expectation over the whole space, right? For everybody. So that's why I call generalization or the true risk. The risk that you actually face once you determine H, what is the true risk or what is the actual loss that you incur. So this is what it is here. Okay, so the problem here, we face problem here. I should do overlay here, but I didn't. So the true risk is not computable. You see that it's not computable because for many reasons. We don't know why. We actually can find H here. I remember this is our approximate function. We don't know why. Right? We don't know the underlying distribution either. So we don't know two important things. So therefore the true risk is actually, or the generalization error is not computable. We cannot operate with that, right? But we want that to be small. So this is our desire, right? We want that to be small, but we cannot operate with that directly. Okay, so that's a problem. Remember, F star is Y. I'm sorry, I use two locations interchangeably. That should be only one. Okay, however, we can use the training set. Okay, we remember what we have. The only thing that we have is actually a training set, right? With N pairs of data. So the question is, what can we do with that? What can we do with that, N pieces of data? So what we can do is actually, we're gonna do approximate our risk. So this is called empirical risk. Empirical risk is Monte Carlo, and this is the reason why we use IID assumption, right? Remember that identically, independently, IID. If you haven't heard about that, then actually I should write down. Sorry. For those who actually do deterministic inverse problem before analysis, this may have an IID. What does mean? So identically, independently, distributed. So let's see, IID distributed. Right? So this is important because when we assume that our data are IID samples of our underlying distributions, we can approximate our risk. We can actually approximate our risk, right? We can approximate our risk here with the Monte Carlo approximations. How many of us here know Monte Carlo? Students and researchers. How many of you know? Don't be shy. None. Okay. Huh? Okay. Yeah. Casino. I'm not so sorry. Monte Carlo. Oh yeah. Casino. Yeah. So actually, yeah. I'm sorry. Yeah, actually, Professor House.